Let's continue on. We have equilibrium. For the most part, virtually everything that we deal with in this course, things are going to be considered at equilibrium. That is, a state really can change as a consequence of a lot of different situations. But when these changes cease, that's when you have a state at equilibrium. We will be considering several different power situations, refrigeration situations, but at every individual state, we will assume that we are at equilibrium. So equilibrium states and equilibrium processes from one equilibrium state to another will play an important role in our thermodynamic analysis. Units are no special item to you. You are completely well exposed to both the SI system and the English system. We will use both. So within the SI system, we have mass, length, time, and force set up as kilograms, meters, seconds, and newtons. We have a pound mass, a length of foot, a time of seconds, and a force of pound force in the English system. So in both of those cases, whether it is SI or English, we could go ahead and state what our force is. F is equal to MA. And whether it's a Newton equal to a kilogram meter per second squared, or a pound force equal to a pound mass times our acceleration, which is in feet per second squared, we will have consistent units. Density and specific volume are used very, very frequently. In thermodynamic situations, we will usually use the specific volume much more frequently than the density. However, the two are completely related to one another. But the density we are going to describe is our mass that we have per unit volume. And if we deal with that in an SI system, our mass per unit volume is kilogram mass per meter cubed, or pound mass per foot squared in our English. The specific volume is the reciprocal of density. And as I had stated already, it is the specific volume that we will use most frequently, and most of your thermodynamic tables are presented using specific volume. Pressure. We've dealt with pressure before in several of our other courses, including even our statics and our stress type courses. Our pressure is a given force that is applied against a given area, and it is our force per unit area. The pressure units, again, are force per unit area that we would have. Frequently we deal with bars, and sometimes we are dealing with our atmospheres, and sometimes we would deal with megapascals. Absolute pressure is relative to a zero pressure at complete vacuum. All of our thermodynamic units are listed assuming a reference frame of absolute zero pressure. Gauge pressure is relative to some other reference. Most frequently, it is relative to atmospheric pressure. When we are dealing with pressures that are greater than atmospheric pressure, we frequently address this as a gauge pressure. However, when we are dealing with pressures that are less than atmospheric, we are then dealing with a vacuum. Temperature is a critical thermodynamic property that we will address all the time. A thermometer. This can be any object at all. It can be any object whose property, some form of measurable property, will change as our temperature changes. That's essentially our definition of a thermometer. We have a thermodynamic property as well as a thermodynamic substance. You could think about a standard thermometer where you have the fluid, which will be the substance. It changes with temperature. It expands with temperature usually. And the thermodynamic property might be the length. So here, consider a glass thermometer. The liquid as the thermodynamic substance and the length as it does go ahead and expand along a narrow channel as the thermodynamic property. You know, thermocouples, there is a change in electrical voltage associated with temperature. Thermistors, there is a change in resistance as a function of temperature. Critical to our work are the temperature scales. You know, the Kelvin scale is the most frequently one used. An absolute thermodynamic temperature scale whose temperature is at 0 degree Kelvin at its base. The differences between Rankine and Kelvin, they differ by a factor of 1.8. Centigrade is a Kelvin scale, but relative to essentially our usage of the freezing temperature of water, or our 0 degrees C. And the Fahrenheit scale, similarly, is at the freezing temperature of water. How do you solve a thermodynamic problem? In very similar ways, it's how you solve most of your problems. You figure out what the problem is, you try to think about it, and you identify what is known. That is critical. Once you find out what is known, state what the problem is. What is to be determined? Try to draw a schematic of it. You will draw that schematic as a physical concept, such as a refrigerator, but you will also draw it as a thermodynamic type situation. What are the changes in temperature, pressure, enthalpy, entropy? These are all used. And you will develop an engineering model which will list what the simplifying assumptions are. Are you at steady state? Are you assuming that the changes in kinetic energy, potential energy, internal energy are or are not significant? Once you have that done, then you can begin to go ahead and analyze or solve the problem.